This e-learning provides important information for the measurement of electrolytic conductivity. Most solids dissolved in water are salts, which increase the conductivity of the water. The increased conductivity results from the fact that water-soluble salts in water decompose into positively charged cations and negatively charged anions. This process is called dissociation. With the supply of an alternating voltage, the anions and cations contribute to the charge transport. This is analogous to the electrons in metals. The more cations and anions there are in the liquid, the higher the current flow. The conductivity of the liquid increases. Conductivity is therefore a measure of the amount of dissolved salts in water. In two-pole conductivity measuring cells, based on the conductive measuring principle, two electrodes are opposite each other. By applying an alternating voltage, a current flow is generated in the measuring medium. The more free charge carriers there are, the higher the measured current will be. The free charge carriers are the anions and cations of the dissolved salts mentioned before. The electrical conductance is determined from the measured current flow using ohmic law. This is the reciprocal of the ohmic resistance. As an example, 2 millisiemens were measured, which corresponds to an ohmic resistance of 500 ohm. The electrical conductance must be multiplied by the cell constant K to determine the electrical conductivity. The cell constant results from the respective geometry of the electrode arrangement and describes the ratio of the distance between the electrodes and their respective surfaces. For the cell in the example, the ratio is 1 cm divided by 1 square centimeter. The cell constant is therefore 1 per centimeter. Multiplying the measured conductance with the cell constant results in a conductivity of 2 millisiemens per centimeter. Cells with a cell constant K of 1 consist of opposing plates or pins. The cells enable measurement in a measuring range from approximately 10 microsiemens per centimeter to 15 millisiemens per centimeter. Cells with a cell constant of 0.1 per centimeter have the same design. These are used in a measuring range from approximately 1 microsiemens per centimeter to 15 millisiemens per centimeter. Cells with the cell constant can also be concentric. Cells with a cell constant of 0.01 have a concentric structure and enable the measurement of very small conductivities in a range from approximately 0.05 microsiemens per centimeter to 10 microsiemens per centimeter. Generally, it should be mentioned that for higher conductivities in the range of 200 microsiemens per centimeter to 2000 millisiemens per centimeter, inductive measuring cells are used. Five connections are available on most transmitters. On the one hand, 4 electrode conductivity cells can be connected to 4 connections. These allow measurement in a measuring range of approximately 1 microsiemens per centimeter to 600 millisiemens per centimeter. Short-circuit bridges are used for the two-pole conductive cells. Because the two-pole cells are used more frequently, the bridges are pre-assembled when the transmitters are delivered. The two electrodes can be connected to the connections as required, with the exception of the concentric cells. For these, the wires of the inner and the outer electrodes must be connected to defined terminals. Shielded control cables are used for the connection and the shield is connected to the transmitter. If there is no separate connection for the shielding on the transmitter, the shielding must be connected to the equipotential bonding. The figure shows the connection of a two-pole conductivity measuring cell to the analysis input 2 of the JUMO Aquis Touch P multi-channel instrument. Shown are the wires for the two electrodes, the short circuit bridges and the connection of the shielding. Conductivity measuring cells are equipped with temperature sensors PD100 or PD1000. In the example, the temperature sensor is connected to temperature input 1. The transmitters available from JUMO can be configured via a program. In the following example, however, the configuration is carried out via the front of the device. The Aquis Touch P is adapted to the two-pole conductive measuring cell. At the beginning, the setting for the temperature input is checked. A PD100 and 2-wire circuit is used. This corresponds to the existing settings. Normally, the conductivity is calculated back to a reference temperature. For this reason, the medium temperature must be available as compensation temperature. The source for the compensation temperature must be defined. In the example, the compensation temperature of temperature input 1 is supplied. Usually, the reference temperature is 25 centigrades. A two-pole conductivity measuring cell with a cell constant of K equals 1 per centimeter is used. With conductive conductivity cells, the so-called relative cell constant must be determined during commissioning and over the operation time with the aid of a calibration. The routine must be released. As described before, conductive conductivity measuring cells are available with different cell constants. These are the so-called nominal cell constants. The effective cell constant deviates from the nominal cell constant. The effective cell constant results from the given nominal cell constant multiplied by the so-called relative cell constant. The relative cell constant is determined by calibration. This must be done during commissioning and, in case of measuring deviations, during the operating time. A test solution with a defined conductivity is used. The conductivity of the test solution depends on the temperature. With regard to temperature dependence, value pairs are indicated on the storage vessel. The test solution should be placed in a suitable container and discarded after calibration. The conductivity sensor with the integrated temperature sensor must be placed in the test solution and the final temperature value has to be awaited. The measuring system must be completely in the solution and there must be no air between the electrodes. The example shows a temperature of 23.7 centigrades. The conductivity of the test solution for this temperature is determined by linear interpolation. The temperature of the test solution is between 20 and 25 centigrades. Over 5 Kelvin, the conductivity changes by 135 microsiemens per centimeter. A Kelvin temperature change results in a change in conductivity of 27 microsiemens per centimeter. The present conductivity results from the conductivity at 20 centigrades, increased by the mentioned 27 microsiemens per centimeter and Kelvin, multiplied by the deviation to the 20 centigrades, thus 3.7 Kelvin. The determined conductivity is given as the reference value during calibration of the relative cell constant. The determined relative cell constant is displayed. This should be within a range of 80 to 120%. If the relative cell constant is outside this range, the cell may be dirty. The cell constant is accepted and calibration is finished. The conductivity of the solution to be measured in the process also varies with the temperature. The present conductivity is the uncompensated conductivity. At different temperatures, there are strongly fluctuating conductivities, and the properties of the measuring solutions are difficult to compare. Normally, the conductivity is calculated back to a reference temperature of 25 centigrades, and this so-called compensated conductivity is displayed on the transmitter. After the slope of the straight line has been entered in the transmitter, it can calculate the compensated conductivity from the uncompensated conductivity and the temperature. The slope or temperature coefficient expresses the percentage increase in conductivity per Kelvin temperature increase. For the determination of the temperature coefficient, it is advantageous if the uncompensated conductivity is known for the typical process temperature and for the reference temperature. In the example, the typical process solution temperature should be 55 centigrades. The conductivity changes from 25 centigrades to 55 centigrades by 240 microsiemens per centimeter. Starting from 400 microsiemens per centimeter, the conductivity increases by 60%. The increase occurs with a temperature change of 30 Kelvin. Looking at the change per Kelvin temperature increase, the temperature coefficient of 2% per Kelvin is obtained. In the example, the typical process temperature is 55 centigrades and the uncompensated conductivity at this temperature is 640 microsiemens per centimeter. However, the compensated conductivity is 400 microsiemens per centimeter. For this to be displayed correctly, the temperature coefficient must be entered in the transmitter. The compensated conductivity is now determined from the uncompensated conductivity, the current temperature, and the entered temperature coefficient. The linear temperature compensation used is suitable for practical use in measuring ranges from 10 microsiemens per centimeter. In addition to the dissolved ingredients, the conductivity is formed by the intrinsic conductivity of the water. In applications such as ultra-pure water, intrinsic conductivity plays a significant role and there are no linear conditions. For ultra-pure water applications, the respective formulas are selected in the transmitters for recalculation to the compensated conductivity. In comparison to the inductive conductivity sensors not covered here, the two-pole conductive cells must be kept clean. In many cases, mechanical cleaning with a brush, for example, is sufficient. If cleaning agents are required, this can be a 2% hydrochloric acid or alternatively acidic or citric acid. After cleaning, the relative cell constants should be calibrated. All information about our seminars, webinars, e-learnings and reference books are available at campus.jumo.net.